The Rolls-Royce RB211 is a landmark high-bypass turbofan engine that represents a defining moment in modern jet propulsion technology, developed in the mid to late 1960s to meet the requirements of the Lockheed L-1011 TriStar wide-body aircraft, and later adapted for multiple commercial and military platforms, including the Boeing 757, 767, and various cargo and military transport aircraft, combining revolutionary engineering concepts with advanced materials science to achieve unprecedented efficiency, reliability, and thrust capabilities. The engine's most distinctive feature is its free-spool architecture, consisting of low-pressure LP spool driving the fan and LP compressor stages, an intermediate pressure IP spool driving the IP compressor, and a high-pressure HP spool driving the HP compressor, with each shaft operating independent at its own optimal rotational speed, thereby reducing mechanical stress, improving fuel efficiency, providing rapid spool acceleration, and ensuring consistent performance across a wide range of flight regimes, a design that contrasted sharply with the conventional two-spool engines of the 1960s, and became the foundational principle for Rolls-Royce's later Trent engine family. During development, the RB211 introduced high-fill carbon fiber fan blades, which drastically reduced weight and rotational inertia, while allowing for larger fan diameters to increase the bypass ratio and overall thrust efficiency. However, these composite blades were initially susceptible to bird strikes and foreign object damage, requiring extensive redesigns, and ultimately being replaced with titanium alloys to meet safety, reliability, and durability standards, illustrating the technical and financial risks inherent in pioneering new aerospace materials and methods. The engine's airflow begins with the large diameter fan, which directs most of the incoming air around the engine core as bypass flow to produce efficient thrust, while channeling a portion into the multi-stage LP, IP, and HP compressors, progressively increasing air pressure before entering the annular combustion chamber, where fuel is injected in precise controlled patterns to maximize combustion efficiency and energy output, while minimizing emissions and thermal stress. The resulting high-energy gases expand through the corresponding HP, IP, and LP turbines, transferring rotational energy to the spools and driving compressors and fan while producing forward thrust, with advanced cooling channels, variable stators, optimized turbine blade aerodynamics, and in later models single crystal turbine blades allowing operation at elevated turbine inlet temperatures for improved thermal efficiency, greater thrust, and longer service life. The RB211 was produced in multiple thrust variants to accommodate different airframe requirements, including the RB211-22B til 37,400, 43,500 lbf, for the L1011 TriStar, the RB211-524 series, 48,000, 60,600 lbf, for the Boeing 757 and 767, and the RB211-535 series til 40,100 lbf, for smaller aircraft, such as the Boeing 727, with key technical parameters including fan diameters ranging from 86 to 97 inches depending on the variant, bypass ratios from 5:1 to over 6:1, overall pressure ratios exceeding 30:1 in later models, multi-stage axial compressors for each spool, high-efficiency HP, IP, and LP turbines, optimized nasal and inlet designs for reduced drag and noise, and digital or analog engine control systems including FADEC advanced variants to enable precise engine monitoring, control, and optimization across all phases of flight. Development of the RB211 was extremely challenging, with early technical issues, production delays, and spiraling costs leading to Rolls-Royce's bankruptcy in 1971. Followed by nationalization by the British government, yet the eventual operational success of the RB211 not only salvaged the company but established Rolls-Royce as a global leader in aero-engine manufacturing, demonstrating that high-risk, innovative engineering programs, while potentially catastrophic financially, can produce transformative technological advancements. Operational, the RB211 proved highly reliable, capable of thousands of flight hours between overhauls, with superior thrust-to-weight ratios, lower specific fuel consumption, high thermal efficiency, and significant reductions in noise levels compared to contemporary engines, while maintenance practices evolved to accommodate the unique free-spool design, composite or titanium fan blades, high-pressure turbine cooling, and multi-stage compressor complexity, establishing a new benchmark for serviceability, durability, and safety. Beyond its immediate applications, the RB211's innovations directly influenced the design and development of the Rolls-Royce Trent family, which continues to power modern long-range aircraft including the Boeing 777, 787, and Airbus A330/A350, incorporating and expanding upon the free-spool concept, high bypass efficiency, advanced materials, turbine cooling strategies, and control systems introduced in the RB211. The engine also contributed to advancements in high-temperature metallurgy, composite engineering, aerodynamic subaxial compressors and fans, annular combustion chamber design, and multi-stage turbine blade performance, making it not only a commercial success, but also a milestone in engineering pedagogy, industrial materials science, thermodynamic cycle optimization, and global aviation standards. In total, the RB211 stands as a towering example of how ambitious design, material innovation, aerodynamic optimization, thermodynamic efficiency, and operational rigor converge to create a high-thrust, high-bypass turbofan that transformed commercial and military aviation, demonstrating how pioneering engineering, even when initially financially catastrophic, can produce enduring technological, industrial, and scientific legacies that continue to shape the aerospace industry decades after introduction, cementing Rolls-Royce's place as one of the world's leading engine manufacturers, and establishing the RB211 as a reference point for high-bypass turbofan design, materials integration, and free-spool efficiency that remains relevant in both historical and modern contexts of jet propulsion and aerospace engineering.